Hello, everyone, and welcome to the online causal inference seminar. We are very excited today to have Neil Davies from the University of Bristol, who will talk to us about average causal effect estimation via instrumental variables, the No Simultaneous Heterogeneity Assumption. After Neil's talk, we will have Tchetgen from the University of Pennsylvania that will lead the discussion. So I will give the floor now to Ying that will be dealing with the Q&A today.
Thank you, Georgia. So we welcome you to submit questions through the Q&A section. If you haven't used it before, it is just at the bottom of the Zoom window. Please submit your questions through the Q&A instead of the chat box for us to better track the questions. I will raise some of the questions to the speaker when we got a chance. Thanks. So I think the stage is yours, Neil.
Okay, thank you very much, everyone. And thank you for the invite and for everyone for coming today. Let me just see if I can get my slides up. Okay, can everyone see that? We're all good? Okay, welcome to my seminar today. I'm going to be talking about a paper that has been under development for pretty much the entire pandemic. It got derailed a bit because Fernando in particular was leading a lot of the pandemic response in Brazil. But it's a paper we're really interested in because it's we think it addresses a key assumption that many genetic epidemiologists are using in their studies. Now, I'm working on the assumption that the audience is quite mixed, we're a bunch of epidemiologists, so George Davies Smith and Limbo and I, we're all interested in genetics and applying causal inference methods to really medical research questions and clinically focused research questions. And there's quite an interesting difference and distinction between the application of some of these methods in economics and econometrics and the way that they've been applied in epidemiology. And really, this is our attempt to see if we can work out how some of the assumptions which have been applied in econometrics maybe differ slightly for the applications, particularly in genetic epidemiology. And what we think we've come up with is a plausible assumption that we can use to identify instrumental variable studies that we think is weaker than many of the assumptions that are used and is particularly applicable to genetic epidemiological studies. And it focuses on the heterogeneity in effect between the instrument and the exposure and the instrument and the outcome. I'll get on to defining it shortly, but I'm very, very happy to take questions as we go. If you want to put them in the chat, I won't necessarily see them, so I don't know if one of the panelists wants to flag them, but yeah, if you've got any questions whilst during the presentation, let me know, and I'm happy to discuss. I should also say that a huge proportion of this work is Fernando's, and particularly the heavy lifting and the innovativeness of it is really due to Fernando. He's a fantastic colleague and brilliant to work with. So without further ado, I'll get on. So I'm going to give a little bit of background about the motivation of why we're interested in this, what other studies have used, what other assumptions studies have used. I'm going to give a brief introduction to Mendelian randomization, what it does and why it's interesting, and why some of the assumptions that we could potentially use in Mendelian randomization differ. So why the field uses different assumptions and what are the implications of that. I'm going to go through a brief description of the core idea assumptions, describe some of the assumptions that have been used in the literature, and then outline what we think we are assuming with our new proposed assumption, which is the No Simultaneous Heterogeneity Assumption. I'm going to present a few simulations, and I'm going to outline how we think this assumption works and what we think we're able to identify in an empirical example that's a Mendelian randomization study. So the background to all of this goes back as a huge history, going back all the way to right in 1928 with the development of instrumental variable models. But the key papers are, of course, Angrist, Imbens, and Rubin's papers describing how we can identify causal effects using instrumental variables in using observational data. Now, pretty early on, in the econometric literature and the economics literature, it was assumed and developed that really the assumption of a constant effect of treatment was pretty implausible for a lot of applications that people might be interested in. In fact, it was taken as read for a lot of the literature that it really wasn't very plausible to assume a constant effect of treatment. So that is that the effect of an exposure has the same effect in every individual. And as a result, many of the instrumental variable studies that have been developed and a lot of the methodology has been done so making assumptions like monotonicity. So that is that the instrument has a monotonic effect on your likelihood of exposure. And Angrist and others have argued that this picks up a very specific treatment effect, which they've described as a local average treatment effect. So that is the effect of the exposure in those whose exposure is modified by the instrument. And this has received a lot of attention in economics, but it's also been kind of translated back into epidemiology and into the clinical literature. And epidemiologists have got super excited about this because a key challenge for epidemiologists using observational data is confounding. And it's been pretty widely understood that observational studies are a pretty unreliable guide for causal inference. And this is highlighted in Miguel Hernan's paper, and this is a really nice description and take which goes through many of the assumptions that were widely used in the literature, including a constant effect of an exposure and assuming a no effect modification of the effects of the exposure by values of the instrument. And this is all has a rich history both that kind of spans both literatures. So in 1986, we had the article by Hurst and colleagues where they were using the effects of the Vietnam draft lottery to investigate the effects on mortality for military veterans. And this is kind of used by Josh Angrist and others as a key motivating example for developing a lot of the instrumental variables literature and methodology. So there's a very nice thread of research that kind of spans both literatures, and it's been quite a productive area. So that kind of gives some of the background in econometrics and economics. In epidemiology, one of the key applications and one of the largest applications of instrumental variable methods is Mendelian randomization. And this is an approach that uses genetic variants as instrumental variables for exposures of interest. And it was originally proposed in the early 2000s, and it's kind of been developed as developing as a literature since then. It was pretty quickly acknowledged that it was an application of instrumental variable analysis, and this has really opened up a lot of different avenues of research, which is kind of taking applications of instrumental variable theory and econometric methods and applying them to large data sets where unusually for instrumental variable analysis, we've got a large number of instruments that we know associate with particular exposures, and we can evaluate in very, very large samples. Not only that, but we can begin to compare the estimates that we're getting from these studies to very large meta-analyses of randomized trials from clinical studies, for example, during the development of pharmaceuticals. So it's quite a nice test bed for a lot of different methodologies, because we can, we've got a gold standard, we've got very, very large observational studies with hundreds of thousands of observations, and we've got a very large number of instrumental variables, because we've got a very large number of genetic variants that we know associate with lots of different traits. As part of the development of this literature, Frank Winnemeyer and Paul Clark published a paper where they outlined the specific assumptions that were required for identifying the effects of an exposure on a binary outcome using instrumental variables. And the key assumptions that they highlight are no effect modification. And they explain how we can use different estimators to estimate a lot of the different parameters that epidemiologists and clinical audiences might be interested in. So specifically risk ratios and odds ratios, which are commonly reported in these literatures. And a typical application of Mendelian randomization is something like BMI and adiposity, or the effects, trying to investigate the effects of adiposity and body fat on coronary heart disease and other cardiometabolic diseases. And we know from very large genome-wide association studies, we've got large numbers of genetic variants that associate with BMI and other measures of adiposity. And we've also got very, very large genome-wide association studies for cardiovascular disease. And we can combine these estimates to estimate the effects of an exposure like BMI on cardiovascular disease. And as a result, one of the key innovations in this literature has been using large data sets of summary data results. So this is where epidemiologists have gone away and collected all of the available data for a specific phenotype like BMI, run a genome-wide association study, and estimated the effects of each individual SNP on that phenotype. And these can be combined in a two-sample instrumental variable framework, where you've got the genetic variant, exposure association estimated in one sample, and you've got the genetic variant outcome association estimated in another. And this can be combined in a Wold estimate relatively easily. And this can also be used to assess some of the underlying assumptions, such as the assumptions around what are called pleiotropic effects. But what's quite interesting about almost all of the estimators that are widely used in this literature is they pretty much universally assume constant effects of the exposure on the outcome. And this is quite unusual, or in contrast to the broader econometrics literature that really has relatively rarely makes that assumption and normally focuses on heterogeneous treatment effects. And the reason why the genetic epidemiologists make this assumption is because it allows them to start thinking about and estimating potential pleiotropic effects, so those alternative effects of these genetic variants. But clearly we can't do that if there are heterogeneous effects of the exposure across, dependent on which genetic variant is perturbating the exposure, because you can't differentiate a heterogeneous effect from a pleiotropic effect. They would look identical statistically. So in econometrics, we've got a literature that's developed using trials or similar approaches. They often assume heterogeneous treatment effects, and they're interpreted as local average treatment effects under monotonicity. In genetic epidemiology, we have got a very large number of very, very weak instruments. We've got this random inheritance of genetic variants at conception, so we're pretty, we've got a plausible natural experiment. We've also got differences because we're dealing with continuous exposures and potentially continuous instruments, depending on how the how everything is coded. But as I say, most of the literature to date has assumed constant treatment effects, particularly when assessing things like pleiotropy. Okay, so that kind of gives a bit of a background of where the literature is up to. This is a basic description of instrumental variable analysis, where we've got a DAG that encodes all of the core IV assumptions. And for the purposes of this presentation, I'm going to be taking all of these core IV assumptions as given. I'm really focusing just on the fourth point identifying assumption. So just so that we're all on the same page, an instrumental variable is something that is associated with a exposure. This is testable. The second assumption is that it's independent of any confounders of the outcome, so there are no confounders of the instrument outcome association. And finally, it affects the outcome only via the exposure, and this is the exclusion restriction. So we can test the first assumption. We know that genetic variants associated with BMI associate with BMI. We can test this in large samples. We can't directly test the other two assumptions, but we can certainly falsify them. So what are the potential fourth instrumental variable assumptions? Well, the first is a bit of a, what's the word? Misnomer, or it's to make no assumption at all. So we can get what are called instrumental variable bounds without making any further assumption about the relationship between the treatment effects and the instrument. The second commonly used assumption is to assume that the exposure has the same effect in everyone. So this is quite widely used in the genetic epidemiological field. Thirdly, we can assume no effect modification of the effect of the exposure by values of the instrument. Fourthly, we can assume that the instrument effect on the exposure is the same in everybody. And fifthly, we can assume that the instrument has a monotonic effect on likelihood of exposure. So this is this idea that the instrument always increases someone's exposure or people's exposure, or always decreases, but you don't get this group of individuals who act in the opposite way to what you might expect. So this is this idea of a group of defiers. The assumption that we are proposing in this paper is the assumption of no simultaneous heterogeneity. So what we focus on is the relationship between the association of the instrument and the exposure and the effects of the exposure on the outcome. If these two effects are independent, so they can vary, but they're independent, then we can potentially pick up and estimate and identify or get an unbiased estimate of the average causal effect across our sample of interest, which is potentially useful because this is a considerably weaker assumption, certainly than the homogeneous treatment effect assumption, and it's also doesn't require monotonicity, and it also gives quite a nice framework for thinking about the plausible assumptions under which we could pick up something that is a reliable estimate of the average causal effect of your exposure of interest in your sample. Okay, so first of all, on the 4-5 assumption, this is these bounds have been widely used or widely discussed in the methodological literature, but not widely used. And I think a quick simulation can illustrate why. So I've created a very, very simple simulation here that just illustrates the typical power that we'd get in a typical study that we might receive. We've got a random instrument Z, a random error. We generate an exposure and an outcome on the basis of this probability function for a sample of 10,000 individuals. I've used Tom Palmer's package just to calculate the bounds. It's really useful and easy to use, but it illustrates that for a sample of 10,000 individuals, the IV bounds that we get are not very informative. So given the parameter values that we've used in the sample, we know that the average causal effect is somewhere between 0.17 and 0.72. So these are as proportions on the risk difference scale. And here you can see on the causal risk ratio scale, the difference between the lower and upper bounds are absolutely enormous. So they're not really very informative. If you contrast this with what you get using two-stage least squares, you can see that by imposing your favored point identifying assumption, you can get much more precise estimates. So while not making this assumption is methodologically appealing, the disadvantage is the level of precision that we're likely to get with these studies is just too low to be in any way informative. And the issue with this is not a power thing. So as we increase the sample size, you can see that the lower and upper bounds stay a similar width. So this isn't something we can solve with greater sample sizes. This is just a limitation of the method, which is not the case if we're imposing our fourth IV assumption. So bounds interesting, but not necessarily that useful for empirical researchers. And there's a really nice paper that's recently come out by Train and Can that have looked into this specifically for two sample summary data Mendelian randomization. So this is where we're using separate samples for estimating the effect of an exposure on an outcome. And really they conclude that the power is unlikely to be great enough to be informative for many applications that we might be interested in. And that's a relatively common finding. So as a result, we need to impose some sort of 4 or 5 year assumption. So the question is, what assumptions can we live with? What assumptions do we think are plausible? So just some notation that's coming directly from our paper. We estimate and we define the individual level causal effects, where we've got a binary exposure, and this is just the difference in potential outcomes. We can get an estimate of the average causal effect in simulated data because we're able to change people's assignment to exposure and to be exposed or not. This estimate is what we're often trying to recover, which is the average effect of an exposure in the population. Now, the instrument of variables estimator, the world estimator, estimates this by estimating the average outcome or the difference in the average outcome in individuals with an instrument whose instrument is valued 1 versus 0, and the difference in the exposure across values of the instrument. And that gets you an estimate of the causal effect in the population. And in terms of the monotonicity assumption, we can define 4 groups of individuals within this population. So first of all, we've got individuals who are always exposed. We've got never takers who are never exposed. We've got compliers who do as indicated by the instrument. The monotonicity assumption assumes that the final group, which is the defiers, the individuals who do the opposite of their treatment assignment, don't exist. And that's how we get identification under monotonicity. Now, what happens when we assume a constant or a homogeneous treatment effect? Well, if the exposure has the same effect in everyone, when we estimate or when we get the IV estimate, by definition, if the effects of exposure is the same in everybody, it's going to identify the average treatment effect. So this is kind of tautological. However, this is often not very plausible for binary outcomes, simply because of the data generating process that you would have to have. And for a lot of applications, it's presumed that treatment effects are likely to be heterogeneous, likely to vary across individuals. So this is quite a strong assumption to impose on our data. So if we're running an instrumental variable analysis and we're having to rely on an assumption as strong as this, it does bring into question the results. So it'd be useful to have other assumptions that are more plausible and less strong. And one of those is no effect modification, which has been widely discussed in the literature. And this is assuming that the effects, so that is the individual level causal effects, don't differ depending on the value of the instrument. So if you varied the value of the instrument, but someone was exposed in both cases, they would still have the same outcome. And this is what's used to identify causal odds ratios and causal risk ratios in structural mean models. And this is a weaker assumption than a constant, than assuming a constant treatment effect. Less widely used in the literature, less widely discussed, is a situation where you've got a constant effect of your instrument on your exposure. Now, the way to think about, or the intuition behind this, is that if your instrument is having the same effect on likelihood of exposure in all the individuals across your population, you're going to be picking out effectively a random or a representative sample of the individual level causal effects across your population. So if you've got a constant effect of your exposure, of your instrument on your exposure, then this too can pick up a average causal effect. We've got a further paper that will flag up in a minute, that's a note on when this is sufficient. So it's a sufficient assumption if your instrument Z is continuous, or both your exposure and your instrument are binary, but it's insufficient if your instrument is binary and your exposure is continuous, and the effect of your exposure on your outcome is nonlinear. But I'm not going to go into detail in that now, and but we do have a paper that goes into that in more detail. So finally, we've got this monotonicity assumption, which is that either if when you increase the value of your instrument, you increase your exposure, or vice versa. And so it's this idea that there are no defiers in your data set. And the interpretation of this, for particularly in genetic epidemiological studies, is less clear than it is for randomized trials or natural experiments where you've got a very clear binary exposure and binary instrument. So for a lot of the applications in the econometrics literature, it's kind of clear who your group of, at least theoretically, it's clear who your group of compliers are. If we translate this to a genetic epidemiological application, we've got it's much less clear who or what the local average treatment effect is and who it applies to, because you have got what's can be coded as a continuous instrument, and you've often got a continuous exposure. So thinking about who the individuals will be is going to be much harder than if you've got a binary instrument and a binary exposure where you can kind of categorize individuals into those 4 groups we discussed earlier. So finally, the Nash assumption really can be thought of as a generalization of and a way to generalize many of the assumptions that we've already discussed. So really going back to our directed acyclic graph, the 2 heterogeneous effects that we're interested in are the instrument exposure association, here indicated by the gamma I, so it can differ across all individuals. And then we've got the effect of the exposure on the outcome, which again can be different for each of the individuals. Now, what we are arguing with the Nash assumption is that it's absolutely critical to consider the correlation between these 2 heterogeneous effects. Because if these 2 heterogeneous effects are independent, what we are in effect picking up with our instrument is a representative sample of the heterogeneous treatment effects of the exposure across the population. So in a situation where we've got a continuous instrument and a continuous exposure, as is pretty common in genetic epidemiological studies, this can be potentially quite plausible in a way that the monotonicity assumption or some of the other assumptions, particularly the constant treatment effect, is less so. However, if there are correlations between the instrument exposure association and the effect of the exposure on the outcome, clearly we're going to begin to get bias because we're going to be picking up a particular subset of treatment effects in our population. So I just wanted to highlight at this point a second paper that we've got on this, which is going through the conditions for when having homogeneity in the instrument treatment effect association is sufficient for the world estimate to equal the average causal effect for a binary exposure and a continuous, sorry, a binary instrument and a continuous exposure. So if you would like to read more, please take a look at that. Okay, so just to summarize the assumptions that we cover in this paper, we've got, first of all, the constant effect of the exposure on the outcome. We've got no effect modification of the effect of the exposure by the values of the instrument. We've got monotonicity, and finally we've got our new assumption, which is no simultaneous heterogeneity. The 3 of these pick up average treatment effects. So first of all, the constant treatment effect picks up an average effect across the population. No effect modification picks up the average effect of treatment on the treated. Monotonicity is only going to pick up a local average treatment effect, and no simultaneous heterogeneity will pick up an average effect across the whole population. So there are other assumptions that I'm not going to cover here. Okay, that was quite a lot of talking. Should we stop for some questions?
Yeah, there is a question popping up saying what to do if either instrument, treatment, or response are ordinal.
That is a good question. If it's ordinal, if you've got an ordinal instrument, that's pretty common. So a lot of the genetic scores that we'd be using would be ordinal, and you can be reasonably flexible in the functional form between your instrument and your exposure, and use those in most of the models. If you've got a ordinal treatment, that is more challenging. one approach would be, it kind of depends a bit if you've got an ordered categorical or an unordered categorical variable. You could potentially define them as two separate exposures and just use a multivariable instrumental variable model if you've got multiple instruments. Which might be the easiest approach. If the response is ordinal, again, if it's an ordered categorical variable, you could use a mean difference model or dichotomize it. I might be wrong. Eric might be able to point you in the direction of some instrumental variable models for ordinal variables. It's probably been done somewhere. Hope that helps. But thanks for the question. Okay, so moving on to the simulation. This is a illustrative simulation that we've tried to make as simple as possible. So I'm going to try and just talk for it, just to explain what we're trying to do here. We've got our exposure x, which is a function of our instrument, and gamma, and you'll see that gamma is a constant here. And we also allow for a nonlinear term. Then we've got two functions which are allowing us to introduce heterogeneity in the effect of our in the association of the instrument and the exposure. So the critical terms here are the delta terms, which are, we can vary. Basically, this function is just allowing us to change the amount of heterogeneity and how that heterogeneity correlates across between the tau variable here and the gamma variable here for x. So depending on the different scenarios that we select, we're able to induce different amounts of correlation. So we can either set it so that there is a homogeneous effect of the exposure, an homogeneous effect of the instrument, or a heterogeneous effect of both, or a correlated effect of both. So the the different scenarios that we investigate are different subsets of modification of the two sets of assumptions. So let me get that out of the way for a second. So we've got scenarios where we've got the exposure causing the outcome, and this is the majority of the ones that we investigate. And then we investigate the whether there are modifications and heterogeneity in each of the assumptions, and we investigate each of the possible pairs. So no modification in or no heterogeneity in either, just modification in the X, Z, the instrument exposure association, just heterogeneity in the exposure outcome association, and then heterogeneity in both. And because it's simulated data, we can then work out the amount of bias that we've got. So this is our first plot where we demonstrate the amount of bias. We've got sample size across the bottom and the median bias going across the y-axis. And what we see for the first 4 scenarios, where we've got homogeneous effects, heterogeneous effects of the instrument on the exposure, but homogeneous effects of the exposure on the outcome, vice versa, and then heterogeneous effects for both parts of the relationship, and having violations of monotonicity, we can see from the simulations that we get unbiased estimates of the average causal effect. It's only when we introduce violations of the no simultaneous heterogeneity assumption, so that is that we've got correlated individual level causal effects of the exposure and of the instrument exposure association. that we get bias. This just shows the median standard error of both approaches, and this shows the coverage, which is really just showing when we've got correlated causal effects, we get problems. So to kind of summarize the simulations, we can get estimates of the average causal effect of the exposure, even if homogeneity, no effect modification, and monotonicity do not hold, which is quite useful. However, if there are correlations between the these two, the gammas, the effect of the instrument on the exposure and the effect of the exposure on the outcome, then we can get problems. So how plausible is the Nosh assumption? Well, so if we take it back to one of our examples, the effect of BMI on coronary heart disease, we can see that under monotonicity or under a constant treatment effect, we're going to get an average effect of BMI on CHD, but we might think that that's not a terribly plausible assumption. Under monotonicity, we've got a local average treatment effect, so it's really talking about the effects of BMI kind of weighted or giving greater weight to genetic variants in individuals with genetic variants of greater effect. Under the Nosh assumption, we need to think about the correlation and the correlations between these heterogeneous effects. So, for example, are the heterogeneous effects of a specific genetic variant, so the FTO variant is quite well known, is the variation in the effect of this variant likely to correlate with any variation in the effects of BMI on coronary heart disease? Now, given that individuals won't know their genetic variant, it's not clear that there is likely to be much of an association there. However, this is a currently untestable assumption. So we think it's a weaker assumption than many of the other assumptions used in the literature, and maybe a reason why a lot of the estimates that we get from models like this and analysis like this have been relatively reliable in picking up causal effects. So I will summarize this. So the No Simultaneous Heterogeneity assumption requires that the instrument exposure associations can be heterogeneous, and the exposure outcome effects can be heterogeneous across the population, but it just requires that those effects are independent. So we've demonstrated that you can get an estimate, an unbiased estimate of the average causal effect, even if many of the widely used assumptions do not hold. We think that many of these assumptions, specifically the homogeneous treatment effects and the no effect modification assumptions, are special cases of the Nosh assumption, and we're kind of treating monotonicity as kind of a separate assumption because it's not attempting to estimate an average treatment effect. But of course, as with the rest of these assumptions, it's not testable directly. So it's still imposing assumptions on our data, but we think particularly for examples in genetic epidemiology or situations where you've got a continuous exposure and many instruments, it's potentially quite plausible and useful. Okay, otherwise, thank you very much for listening, and I'd like to open it up to questions and acknowledge my funders and my fantastic co-authors.
Thanks, Neil. So we have two questions. I think the first one is related to scenario 5 in your simulations. It asks whether the following setting will violate Nosh, which is unmeasured confounder U modifies both the effect of the IV on X and the effect of X on Y.
That is a good question. If we go, maybe it's easiest. Sorry, my computer is not loading itself. There we go. So if we go back to this one. So we've got an unmeasured confounder U that modifies both the effects of the instrument on X and the effect of X on Y. Would that violate Nosh? I think that would introduce correlations between these two parameters. So if you've got a confounder that affects both gamma here and beta here, that's almost certainly going to introduce correlations. So yeah, I think that would be a pretty clear violation, I think.
Thank you for your answer. So I think we have only a limited amount of time. So we'll move to the discussion by Eric, and after the discussion, we might have more time for a Q&A.
All right, let me share my slides. Okay, can everyone see my slides? So thank you, Neil, for the interesting presentation, and thank you to the organizers for the invitation to discuss this paper. Let me just get right into it. So as Neil mentioned, IV requires a set of assumptions, and it's best summarized by this simple DAG. You need the IV to be relevant with respect to their exposure. And just to confuse people, I'm using a different notation. A is going to be the exposure, Y the outcome, and G for genetics is the set of IVs, and U the unmeasured confounder. And so we have our three assumptions that are stated here. I'll refer to them as IV1 through IV3. It needs to be relevant for the exposure. It needs to be independent of the unmeasured confounder, and it needs to have no direct effect on the outcome, not through A. And as Neil mentioned, these are not sufficient for point identification in general. One needs an additional fourth assumption for point identification. And depending on the nature of this fourth assumption, one obtains a very specific type of treatment effect under the additional three IV assumptions. For instance, he mentioned monotonicity, which essentially requires the inequality holds, that the effect of the IV on the exposure at the individual level is monotone, almost surely for every individual in the population. And this leads to identification of the well-known late causal effect. The advantage of this is that it does not restrict heterogeneity of causal effects. However, it identifies causal effects for an unidentified subpopulation and does restrict the treatment assignment heterogeneity. This is not often recognized, but in fact, it's fair to say that, as indicated by the title of this slide, IV identification actually requires that heterogeneity is not pervasive, one way or another. And what I want to demonstrate here is that, in fact, this assumption that heterogeneity is not pervasive can be moved from the outcome model to the exposure model to the selection bias quantity. And all of those three are just a reflection of this fact that you need to have some kind of extrapolation for IV to make sense. And so one question is, how does monotonicity restrict the exposure model? Well, it's useful to use a really nice result from Vitakli back in 2002, who established an equivalence between two models. One, which is the Imben, Sangris, and Rubin result with monotonicity expressed in terms of potential outcome, versus so-called latent index selection model, where they explicitly state that the selection into treatment is triggered by this threshold model, where delta is an unobservable. And the assumption here is that the IV is independent of the joint counterfactual outcomes and the error, the latent factor of the selection model. And this is, in fact, homogeneity assumption at the unit level, in the sense that you can imagine that I could generalize this model to allow this function P of G to be non-separable in the errors, so that, in fact, it triggers different response for individuals with different values of delta as a function of G. In that sense, monotonicity is also a homogeneity assumption on the first stage. Now, moving away from the late, as Neil mentioned, one might want to estimate or identify the effect of treatment untreated. Robbins in '94 established that there again, homogeneity gives you the result. And the homogeneity assumption that he makes in his work is that, in fact, the causal effect among those who receive the instrument G equals 0 and are treated is the same as the causal effect among those who receive G equals 1 and also are treated. And one nice thing about this assumption is that it always holds under the null hypothesis, but in general, away from the null, it might or may not hold. But if you have it, if it does hold, he's able to establish that the wild statistic actually identifies the effect of treatment on the treated. With Steen and I wrote this paper back in 2013. It's a technical report. It's on the web. If anyone is interested, we never actually got it published. And we showed that, in fact, you can move this homogeneity assumption from the causal effect part of the model to the selection bias part of the model. And it's a nice assumption in the sense that it's relatable to other assumptions. So in fact, if you look at the association between the counterfactual under the treatment-free counterfactual outcome among the treated, for different values of G on the additive scale, the assumption essentially requires that that association is the same as for untreated individuals. And so one way to think about this is, in fact, this is a form of parallel trend assumption, which is familiar to the DID, that the change in the DID G is time, essentially. That the change in your potential outcome in the treated as G evolves is the same as in untreated. Another way of interpreting this is actually looking at moving this term to the left-hand side and this term to the right-hand side, in which case you're looking at the difference between the potential outcome and the treatment, conditional on G equals 1. And that's, in fact, how strongly is the potential outcome associated with the treatment. That's quantifies the amount of departure from the assumption of no unmeasured confounding, because no unmeasured confounding would say that that difference is exactly 0. And so what the assumption here says is that the selection bias is present. It may not be 0, but it's homogeneous in levels of G, for G equals 1 and G equals 0. That the IV is balanced with respect to that selection bias is balanced with respect to the IV levels. And so it has this dual interpretation that I think is very nice. And the advantage is that it allows for unrestricted effect of treatment untreated, unlike Jamie's assumption. However, this assumption now must hold even under the null of no causal effect, similar to the parallel trend assumption in DID. Now, turning to the topic of actually today's talk was the ATE, and I want to relate this kind of to the literature on the ATE with Ivy, because there are actually many results that have hinted to or have established the results that we discussed today. So some work with Limbo Wang, the co-author of the Nosh paper, we established back in 2018 that if you consider an IV4 assumption, whereby these are essentially quantities that appeared in Neil's presentation, I look at the causal effect condition on the unmeasured factor U, and so that quantifies the heterogeneity, the amount of heterogeneity in the causal effect as a function of the unmeasured factor. And I can likewise look at the association between the IV and the exposure on the additive scale as a function of U. And essentially, in what we showed was that if in fact the covariance between these two quantities is 0, which can happen under many scenarios, then one can identify the average treatment effect. And we can refer to this as NUSEM. So I have a few questions for Neil. The first question is, Nosh appears stronger than NUC-M in the case of binary A and G, as it requires homogeneity assumption at the Nash requires homogeneity at the unit level, as opposed to NUC-M, which requires homogeneity at the average level. We're looking at the conditional mean given you. So we take the expectation before looking at the covariance. Oops, sorry about that. The second, and I wonder if he agrees with this assertion or if I'm missing something. The second question is, although the covariance between these two association measures or heterogeneity measures appears is symmetric, obviously it's a covariance, identification is actually not symmetric in those two, in the following sense. That, for instance, to illustrate this, if I were to assume that the outcome causal effect is homogeneous, that yields only identification of the ATE, of the contrast, of the effect measure. While if I'm willing to assume that the effect of the IV on the treatment is homogeneous, that actually identifies the entire distribution of YA, not just the causal contrast. And in fact, it therefore identifies the potential outcome mean. And in fact, it identifies any functional. So if you wanted to fit a Cox model, you wanted to fit any nonlinear model, a quantile regression, no homogeneity assumption or separability of the errors is required for the outcome under this assumption. And so it's a much stronger assumption in many ways, in the sense that it delivers a lot more. And so I'm curious whether there's a similar asymmetry for Nosh. The third question is kind of a remark and an aside and maybe pedantic, but what does Nosh mean for binary A and continuous G? In the paper, it appears the theorem is stated by taking the derivative of the treatment with respect to the IV, which is of course not well defined if A is not differentiable. I think this was a sort of hinted at by a question from the audience earlier on. And finally, the last question / comment, and I'll leave these on for in case Neil does not remember. There are a lot of comments and questions here. What they are, in what order. In what sense is Nosh necessary? And so for continuous A, Nosh requires that in the paper at least, and I think Neil briefly covered this, but in fact, for continuous A, they actually require that the outcome is linear in the exposure. The potential outcome is linear in the exposure. But this is actually maybe unnecessary under a mild strengthening of Nosh. For example, consider there's a very well-established literature in econometrics known as the control function approach, which essentially requires that there exists a mapping which takes in as arguments your exposure and your IV, and returns essentially a modified treatment, such that conditional on this transformation, you actually have unconfoundedness. Okay, so if this holds for A continuous, I'm only focusing on A continuous, that if you have such a mapping, then you've created a new variable that will allow you to control for confounding. And then you can identify the average counterfactual mean. It's completely non-parametrically identified. And so you need not assume that Y is linear in A. By simply using the G formula with this alpha A of G or AC as your control variable, as your variable adjusting for confounding. To crystallize this idea, it's a very simple idea. Consider the following system of equations where my outcome is unrestricted, it has its error, and my exposure follows this additive error model. This is a special case of Nosh, because this model for the treatment given G is completely unrestricted. However, I'm not assuming epsilon delta independent, because that would be assuming non-measure confounding conditional G. And so you allow them to be correlated. However, the IV is independent of both. And that's a reasonable assumption for the IV. And then one can show, Blundell and Powell back in 1999 established that in fact the transformation which basically demeans A. So you fit a non-parametric regression of A given G. If G is binary, that's easy to do. If G is continuous, use kernel of polynomials, a flexible model. Take the difference between the two, and whatever is left is an estimate of delta, and that delta is in fact a valid AC and you could then use in a second stage to adjust for confounding under standard, using standard methods to estimate the G formula. And so the control function approach, it was recently, in fact, rediscovered by Burgess in 2014, and I think Neil was also a co-author of this paper. And it seems like in MR literature, under assumptions that the first stage is actually linear in G, which is unnecessary in this case. And I do think it would be nice in this literature as we keep evolving to connect it to existing literature. And so there is a very rich literature in econometrics about the control function approach. And lastly, I wanted to mention that Invents and New, in fact, relaxed this additivity, the separability of the errors that I made here. Oops. And allow for a more general model in the sense that the model may not be separable in the error as long as it's monotone in delta. Then the control function is just the cumulative CDF of the treatment given the IV. And again, you can estimate this non-parametrically and use it as a control function to adjust for confounding. The outcome model need not be restricted at all. And so this appears that this claim that Nosh or a version of Nosh is not sufficient for identification when A is continuous. I think we can relax that if we're willing to not just require that the covariance be independent, which is what Nosh requires, but rather that we can recover a control function approach. So this is not exactly a contradiction of their results. It doesn't contradict it because the assumptions are not exactly the same. However, it shows that a lot more is actually attainable under a slight strengthening of the assumptions. And so maybe I can stop there, 2 minutes over, and hear if any response from Neil. Thank you so much.
Thank you, Eric. You can keep those questions up so that we can have Neil maybe give some responses.
Wonderful. Thank you very much, Eric. Yeah, I greatly appreciate your thoughts on this. So just to take your questions in turn, I've not read the Nuclem paper. How do you pronounce this assumption?
Yeah, that's fine.
In detail. So I don't know whether I need to look at the paper to come to an informed view on which is stronger. But I would be interested in looking at that in further detail. But yeah, just from what you said, I don't know is the quick answer. So for question 2, I'm inclined to agree with your proposition here, that I think it probably is a more useful, I don't know whether I describe it as stronger, but potentially more useful assumption if you can demonstrate that the instrument exposure associations are constant. It's going to get you, is going to be able to identify more. For question 3, I'm not sure I've followed quite what you're getting at here. Can you elaborate?
Sure. Yeah. So in your paper, when you state the actual result, you define in a case where G is continuous, you work with this quantity, including when A is binary. So if A is binary, A as a function of G is not differentiable. So this derivative doesn't exist. And so there was a little bit of disconnect between, working Nosh was based on this definition, because it says this derivative needs to be uncorrelated with the first stage derivative of y with respect to A. But it's unclear what it's unclear what that actually corresponds to as objects, mathematical objects, because A is not differentiable if A is binary. It takes values 0 and 1. It's not continuous. But we can leave this aside. It's more of a pedantic. I think the argument still goes through, but I think it requires some care in how things are defined.
Yeah, I mean, we don't specify that particularly strongly in the paper, but you're right, it'd be worth looking into and perhaps elaborating on that in the paper. And the final question is a really good one. I mean, so I'm trying to be very clear that there's lots of potential assumptions that we could use here, and Nosh is just one of them. So I don't think Nosh is necessary in any way, shape or form, right? There are many, many other assumptions that you could use. So it's really a question about where will it be useful and what can we learn from the Nosh assumption? I think it's potentially quite a nice framework, an intuitive framework for interpreting when these estimators are likely to work and really interrogating what we mean, because it's very, very simple, all right, as to explain what the assumption we're making and to go through potentially applied examples and evaluate how plausible it is about what we're picking up. So I think it has a certain intuitive appeal about it. So just specifically on this 4th question, the linearity I don't think is in any way necessary for our results. So we've shown some nonlinear models of nonlinear data generating processes, and it.
Which linearity?
So
you have 2 models.
Yeah, so in the exposure outcome effect and relationship.
Well, that's the paper you put up, right? You have this paper that says independence here is not enough, and you in fact say in your paper that this model needs to be linear in A when A is continuous.
So yes, that's the second paper that Fernando put up. But in the first paper, we do investigate nonlinear exposure outcome relationships, and that appears to be fine. So I suspect that the linearity in the second stage is not necessary, as far as I'm aware. And the next comments?
I think it's part of the same comment. It was basically, but anyways, thank you. It's just pointing out. Yeah, go ahead.
I'm sorry to break up the party, but we're running a little out of time. So if I can we can wrap up the seminar, and if you'd like to discuss more, we have more time afterwards.
Okay.
Sure.
Well, thank you very much for the comments, Eric, and for everyone's comments in the chat. I'm happy to stick around and answer some of these and continue the discussion if there's interest and people would like to stay on. All
right, just to quickly thank you all for being here. Next week, we have Alex Lutke from the University of Washington that will be talking to us about adversarial Monte Carlo meta-learning of conditional average treatment effects. Thank you for your time, and we hope to see you next week.